Good day, everyone. My name is Julius Adonai. With me are Mr. Bernabe, Mr. Pedregosa, and Mr. Salangi. Let me express again our gratitude to our panel members and advisor for giving us the opportunity to make this defense possible. So without any further ado, may I present our thesis titled Energy Analysis and Development of Conservation Plan on the Administration Building of Mapúa University Intramuros through Applied Open Studio and Energy Plus Simulation software. We'll start off with a brief background about our study. Based on the Department of Energy of the Philippines, the building sector is one of the most energy-intensive sectors of the national economy, accounting for about 15 to 20% of the total energy consumption. Throughout the years, energy costs have gradually increased due to the depleting energy sources, especially in the non-renewable sectors. Electricity costs, however, can be reduced by properly conserving energy, by strategic planning, identifying what should be improved and what are the cost-effective and energy-efficient solutions and approaches will be easier that will consequently save time, money, and energy. With the help of this software, we could achieve that goal. Mapua University is bound to have a large energy demand due to the amount of lighting power density, HVAC system, overall electricity used for laboratories, classrooms, and offices. In RA 11285, it is stated that the Commission on Higher Education must incorporate appropriate energy management courses into existing energy curricula. It would also encourage higher education agencies such as universities and colleges to adopt energy savings initiatives. The general objectives of this study are to assess the energy consumption of the administration building and introduce an energy conservation plan that will optimize the energy performance of the building. Specifically, we will conduct an energy survey and energy analysis of the facilities and equipment used inside the building. We will then simulate the building energy performance using the data from the energy survey and energy analysis. Afterwards, we will determine the potential energy saving solutions to reduce energy usage and enhance the energy efficiency of the building. And finally, simulate the BEP with the application of the proposed energy conservation plan. This study may help reduce the amount of fossil fuel use, carbon dioxide emissions, and electric consumption of an establishment. Efficient modification and utilization of energy-consuming products can limit energy waste and carbon dioxide emissions. It can also protect the environment in support of the economic and social development goals of our country. The study will consider the administration building as the focus for the energy analysis and energy conservation plan. The data that will be audited will be limited to the data of electric use and consumption, ACU, plug-in equipment, lighting inventory, and the building floor plan provided by the Campus Development and Maintenance Office. Lastly, the simulation will consider the following parameters: lighting power density, indoor personnel density, indoor design temperature, outdoor air temperature, location, plug-in equipment, air conditioning units, schedules, holidays, and the building surfaces and construction. That ends my part. Let me call on Mr. Salangit to discuss the review of related literatures.
Thank you, Mr. Adona. Now let's move forward to the reviews of related literature. So for Energy Plus, we use this following software to guide us on how to operate software like setting up the weather profile and etc. For Open Studio, we use this literature to help guide us on how to make our thermal load and how to plug into the Energy Plus. And for the standards, we use this literature to have a basis on what is the current standing of the admin building of Mapúa and how to further optimize it. Now, let's continue to Chapter 3, which is the theoretical considerations. First one is heat transfer. There are three types: conduction, convection, and radiation. Conduction is the transfer of energy between a more energetic particle to the adjacent, less energetic particle. We use the formula Q subcond is equal to negative Ka times delta T over delta X, where Q subcond is equal to the rate of heat conduction in watts, K is the thermal conductivity of the material in watts per meter Kelvin, A is the area per meter squared, delta T is the temperature difference in Kelvin, and delta X is the thickness in meters. Convection is the energy transfer between a solid surface and the fluid traveling adjacent to it. We use the formula Q convection is equals to H times A sub S times T sub S minus T sub infinity, where Q convection is the rate of heat convection in watts, H is the convection heat transfer coefficient in watts per square meter Celsius, A sub S is the surface area in square meter, T sub S is the surface temperature in Celsius, and T sub infinity is the temperature of the fluid sufficiently far from the surface in Celsius also. The last one is radiation. Radiation is the change in the atomic configuration of the atoms or molecules produced by electromagnetic waves. The formula we use is Q rad is equals to epsilon sigma A times T raised to the fourth, where Q rad is equal to the rate of heat radiation in watts. Epsilon is the emissivity of the surface. Sigma is the Stefan-Boltzmann constant, which is 5.67 times 8 raised to negative 8 in watts per square meter times Kelvin to the fourth. A is the area in square meter, and T is the surface temperature in Kelvin. The next one is air conditioning system, air handling unit, and ventilation system. Let's start with the air handling unit. Air handling unit is an equipment used to recondition and circulate the conditioned air in a large-scale building, providing heating and cooling. We use the formula for cooling and heat rejection, which is F sub SA is equals to F sub RA minus F sub EA plus F sub FA, where F sub SA is equal to airflow rate of supply air, F sub RA is equal to the airflow rate of return air, F sub EA is equal to the airflow rate of exhaust air, and F sub FA is equal to the airflow rate of fresh air. The next one is dehumidification. It is a process in air handling unit that removes moisture, water vapor, and the humidity from the air while maintaining the temperature of the dry bulb stable. So when the air at a given dry bulb and dew point temperature is cooled below the dew point temperature, a cooling and dehumidification process begins. Now, for the air conditioning system, we use the formula EER is equals to Q sub C over Q sub I, where EER is equal to the energy efficiency ratio, Q sub C is equal to the cooling capacity in kilojoules per second, and Q sub I is equal to the power input in watts. Another formula we used is COP is equals to Q sub cold over W, where COP is the coefficient of performance, Q sub C is the heat removed in watts, and W is the work done to remove heat in watts also. So let's move on to the ventilation system. In here we use the formula Q sub S over rho times C sub P times T sub 2 minus T sub 1, where Q is equal to the ventilation rate in cubic meter per second, rho is the air density in kilogram per cubic meter, Q sub S is the sensible heat gain in watts, C sub P is the specific heat of air in joules per kilogram Kelvin, and T sub 2 minus T sub 1 is the total temperature rise of incoming air in Kelvin. Now we have here is the energy consumption cost. It is defined as the energy that is utilized to produce an action, manufacture something from parts to a whole, or simply air condition a place or establishment for inhabitancy. Energy consumption cost can be determined by knowing the wattage of the appliances based on its manufacturing label, average number of hours it was used per day, and the price of kilowatt per hour of electricity as per your local electrical distributor. So in energy consumption cost, we use the formula E is equals to P times T times X per kilowatt hour times 30 days, where E is the energy consumption cost in peso, P is equal to the power in kilowatt, T is time in hour or day depending on you, and X is the price per kilowatt hour of electricity issued by your local distributor. Next part is the improving of energy consumption and efficiency. So the building sector in the Philippines is one of the most energy intensive sector of the national economy, accounting for about 15 to 20% of the overall electric power consumption. So to prevent potential energy crisis because of the growing building sector, the Department of Energy published a guideline that aims to optimize the energy consumption for the future and existing building. So first one is lighting. Lighting system shall provide comfortable visual that meets the required amount of lighting intensity for expected activities with minimal energy requirements. So meaning higher illumination levels used are likely to waste more energy, but lower levels could impair visual effectiveness. In a lighting design practicable room, surface reflectance should be considered, like dark surfaces should not be used or avoided since they absorb light. Lighting system should be coordinated between daylight and artificial lighting. Overall lighting power density for building interiors and exteriors shall not surpass the allowable maximum values for building areas. Emergency and security lighting must all have a manual, automatic, or programmable controls. So this slide shows the tables used for lighting. So the table on the left shows the task, the minimum and maximum lux, and applications. The table on the top right shows the lamp type, rated power ranges in watts, efficacy ranges lumens per watt, and minimum polar rendering index CRI. And the lower right table shows the surface and the percent reflectance it allows. The next table shows the area or activity and the lighting power density in watts per square meter. And this table shows the building area or space and its respective lighting power in watts per lumen. So the next one is ventilation. So the amount and quality of air used to ventilate spaces shall always be exact to cater human occupation. All air conditioning system and equipment shall be sized close to the required size produced by doing the system load calculations. So these are some samples. So chilled water system, if it's 200 TR or less, so you have to have a minimum of 2 chiller units. Above 700 kilowatts to 4,218 kilowatts or 1,200 TR, you have to have a minimum of 3 chiller units. Above 4,218 kilowatts to 8,787 kilowatts or 2,500 TR, you should have a minimum of 4 chiller units. And above that, depends on the good judgment of the design engineer. So the chilled water piping should be thermally insulated. Insulation should be required for chiller surfaces like the evaporator shell and compressor suction line. All insulation covers should be vapor sealed also. Exception to pipe insulations are pipes that convey fluid that have been cooled using fossil fuel or electricity, and pipes that have fluid temperature ranging from 20 degrees to 40 degrees, and pipe that does increase in energy consumption when not insulated. So let's move forward to thermal model. Thermal model of the administration building is to be built with the use of Energy Plus Building Energy Performance Simulator. Features of using Energy Plus BEPs are accurate representation of thermal mass effects, with the use of OpenStudio for Google SketchUp, and a control model geometry can be constructed with the use of text editor. You can also see the comparison between the system load and the space load at every time step because of the sub-hourly calculation and heat transfer reporting. Another feature is the model is configured to output heat flux for major envelope and internal load characteristics studied in the analysis, such as infiltration, ventilation, conduction through inside wall surface, conduction through inside floor surface, conduction through windows, transmitted solar gains, lighting power, and equipment power. So the last part is the lumen method. Lumen method is also called photometrical computation and is commonly used for interior lighting calculations. It is used to determine the total number of lights needed to produce a specific number of illuminants. The formula we used is N is equals to E times area all over lumens from each luminaire times MF times UF, where E is the illuminance level chosen based on the IAS recommended lighting level, area is the working area to be lit up, lumen from each luminaire is the output of the chosen luminaire in lumens, MF is the maintenance factor or light loss factor. Depends on the maintenance of the building, but in general, it has a value of 0.8 to 0.9. UF is the light flux reaching the work plane, which is always less than the lumen output, since some of the light is absorbed by the various texture around the area. UF is always a number less than unity, and a typical value is from 0.8 to 0.9 from an old to modern type of office building. I would like to call on Mr. Jeremy Pedregosa for the next following chapters.
Hello everyone, I will be discussing the methodology. As you can see here, this is the process flow diagram. We started off first with data gathering, which includes the walkthrough survey and the building energy utilization analysis. Next, we will be 3D modeling with the use of OpenStudio plugin on SketchUp. Next is the initial simulation, where we are going to obtain the energy baseline. Then we are going to develop an energy conservation plan, which includes selection of improved lighting and reallocation of ECUs. And next, there will be a final simulation, which includes the implemented energy conservation plan. And then the data from both simulations will be compared to, and the researchers will draw conclusions and recommendations. So the researchers started data gathering by going to the site and obtained data such as building envelopes, window locations, and as well as door locations. The researchers obtained information such as schedules of occupancy on various rooms and as well as energy consuming products such as equipment and lights. For the creation of the 3D model, the researchers obtained a floor plan from the CDMO, which then was simplified for it to be imported in the 3D modeling software. As you can see in the next slide, this is the 3D model created in SketchUp with OpenStudio plugin. So as you can see here, this is the flow process diagram for obtaining the energy baseline. So in the initial simulation, we started importing the 3D model from SketchUp and OpenStudio plugin to Energy Plus alongside with the weather data from the Internet of Manila. So the input parameters in Energy Plus are the schedules, such as occupancy of rooms, equipment usage times, and lighting times as well. Internal gains, which are the people, and as well as energy consuming products such as equipment and lights. Next, after simulating, we will have an output of site and source energy, end uses, HVAC sizing, and equipment sizing. Next is developing an energy conservation plan. So in this energy conservation plan, the researchers will be selecting improved lighting by using the lumen method. The researchers will be swapping out the light bulbs or outdated ones for LED light bulbs. Next is the reallocation of ACUs, as well as the removal for ACUs in rooms with excess cooling. Next is the final simulation. So as you can see here is the flow process diagram for recalculation of end uses. So the end uses are cooling, lighting, and fans. The parameters used for this simulation is the energy conservation plan, which is improved lighting, removal of ACUs, and reallocation of ACUs. Then lastly, we'll be comparing the data between the baseline and the improved and draw a conclusion. So as you can see here is a comparison of end-use energy consumption. The end uses will be cooling, lights, and the fans. We'll now be discussing the results and discussions. So as you can see here in this slide, this is the site and source energy and the end users results of the Energy Plus simulation of this. So this will be the energy baseline. So as you can see here, the site and source energy, the site energy is 31.5% and the source energy is 68.5%. Then lastly is the end uses, where the majority of the end uses is the interior equipment, whereas 13.7% for the cooling and the lighting uses only 8.33%. And lastly, the fans, which is 4.07%. As you can see here, this is the total cooling demand per month. Based on the data, the third floor has the most total cooling demand per month. This is due to the fact that the faculty room present in those floors have the different schedule compared to the office hours of the other floors. Next is the total cooling demand per square meter. So based on the data, the most total cooling demand per square meter is the fourth floor. This is because the fourth floor has the least amount of area compared to the other floors. So I will now be talking about the HVAC sizing. So this is the first floor HVAC sizing results. So the blue bar indicates the amount of cooling load required by that room, whereas the orange bar indicates the excess cooling load indicated in that room. So this whole bar here, the combination of the orange bar and the blue bar, is the current cooling load present in that room in the baseline. So next is the second floor. These are the results, almost the same as the first floor, that they have excess cooling load. Whereas in the third floor, likewise, there are quite a lot of excess cooling load. And lastly, fourth floor, which has actually insufficient cooling compared to the other rooms in other floors. The Do It B and Do It servers actually have insufficient cooling compared to the other rooms, which only have excess cooling load. In developing an energy conservation plan, the researchers were able to use the lumen method to create a new inventory for replacement for the luminaires. So as you can see here are the floor layouts of the first floor and second floor, the third floor, and the fourth floor. So these floor layouts indicate the positions or the placements of those luminaires. So in the legend you see here is the 30 watt, the 24 watt, the 22 watt, 20 watt light bulbs, and so on. Next is the floor layout of ACU units. So this is the floor layout for the new positions or locations of those ACU units. This is because there are units removed and there are units reallocated to different floors. So these are the new positions. This is for the first floor, the second floor, the third floor, and the fourth floor. So in the legend, the yellow box is the ductless air unit, the split types, and as well the orange is the floor type, which is only present in the seminar room. Lastly, this is the comparison of the end uses for the baseline and the improved one. So originally, we have 143,736.31 kilowatt a year. When the energy conservation plan was implemented, we only have 125,558.49 kilowatt hour per year. That is a difference of 12.65%. The school can actually save 163,809.42 pesos. So these are the graphs here. As you can see, the end uses comparison graph and as well as the total end uses comparison graph. So this is the overall of kilowatt hour per year at the right side. And that is all for results and discussion. May I now call on Mr. Bernabe for the conclusion.
Good day to all. I'm Edison Bernabe, discussing Chapter 6, which covers the conclusion and recommendations. For the conclusion, the researchers were able to conduct an energy survey and energy analysis of the equipment and facilities used in the administration building by conducting a walkthrough survey and using the Lumen method. Based on the survey, the administration building categorized itself as Type 1 establishment in RA 11285 with a total energy consumption of 550,952.8 kilowatt-hour per annum. The researchers did a walkthrough survey which the specifications, brand, and list of equipment, ECUs, and number of lights per room were gathered. To have a precise 3D model, the researchers measured the actual dimensions of the window. The use of Lumen method, the researchers determined the required number of fixtures per room. These data gathered were used in the simulation to reduce the energy consumption of the building. The simulation of building energy performance was done by the researchers using the Energy Plus and OpenStudio. The data from energy survey and analysis were applied as the parameters in Energy Plus, while the dimensions and plan layout were used to make a 3D model of administration building in OpenStudio. From the simulation, the researchers determined the end use, cooling, lighting, and fans energy consumption at fully operational. In HVAC and equipment sizing, the researchers determined the cooling load and COP per room. These were used in optimizing the new HVAC design of the building. The researchers were able to create potential energy-saving solutions to reduce the energy consumption. The solutions were to remove all non-inverter ECUs and ECUs with excess cooling to rooms. Next was to reallocate ECUs to rooms with poor cooling condition. For lighting system, replace all fluorescent bulbs with LEDs to enhance energy efficiency. The researchers were able to simulate the building performance with the application of the proposed energy conservation plan. The percent differences were obtained after the simulation as shown in the table 5.22. It is recommended to replace all non-inverter ECUs with inverter-type ECUs to reduce the energy demand for cooling. Moreover, it is important to follow the concept of R3-90-1 to enhance the energy efficiency of the building. The researchers recommend the users to have an updated version of the simulation tools that will be used. It should have a feature that is reliable and easy to use. Moreover, the researchers recommend that equipment usage must be optimized, such as turning them off when not using. In lighting system, it is recommended to use LED bulbs as they are more efficient than fluorescent bulb. Adding motion sensor and dimmers will reduce the energy consumption when in occupancy. That ends my report. Thank you for listening.